Solving a system of equations simply means taking more than one equation, in this case 2, and solving when they will be the same. What value for x and y can you plug in that will make both of these equations true at the same time? Let's try the graphing method first. If I were to try to graph each of these, I'm going to find out where are these the same, where do they intersect. The first line, y equals 3x, is in points slope-intercept form. 3x plus 0. So I'm going to start at 0 and follow a slope of 3 all the way across my graph. And I can draw in the line. My second equation, however, is in standard form. Standard form graphs are a little bit harder to make, but what we're going to do is we're going to find both the x and y intercept. So if I plug in a 0 for the y, that will give me what x is, my x-intercept. So y is a 0, and I try to solve. That's 2x equals negative 6, divide by 2 on both sides, and x is negative 3. That's 1 point for my graph. The second point will be if I start fresh with my equation, 2x minus y equals negative 6, and instead plug in a 0 for the x, which means I'm solving for y, to find a y-intercept. So negative y equals negative 6, divide by negative 1, and we get y equals a positive 6. I can plot both of these points on my graph paper. An x-intercept at negative 3, so negative 3, 0, and a y-intercept at positive 6, so go up to 6, and draw in my line. I notice that both of these lines have the same slope. They are both rising at a rate of 3. Therefore, these lines are parallel. They are never going to intersect, and we say that there is no solution. Let's try solving one more with the graphing method. Let's look at our first equation. 5x minus y equals negative 15. So I'm going to start by finding both x and y intercepts. So I can plug in a 0 for the x, I can plug in a 0 for the y, and then plot the points. If x was a 0, negative y equals negative 15, or the y would be positive 15. If y was a 0, 5x equals negative 15, divide by 5 on both sides, and x would be negative 3. I can graph my first line. 0, 15. Ooh, it doesn't fit on my graph paper. All right, now I've got a scale of 2, so I can fit 0 up to 15, and to 0, negative 3, and draw the line. And now I can graph my second line. Plug in a 0 for the x and a 0 for the y and see what happens. If x is 0, that says y equals negative 3. If instead y was a 0, we'd have x equals negative 3. That's tricky. Both the x and y intercepts are at negative 3. So I'll put an x-intercept at negative 3 and a y-intercept at negative 3. Draw the line through. We can see that the point of intersection is here. So solving the system, the values that make these system of equations true would be when x is negative 3 and y is 0. If you wanted to double check your work, you could go back to your original equations and plug in those values and make sure it comes out true. Lastly, we'll go through an example of substitution and elimination. For substitution, you need to first always pick one equation to solve for a variable. I'll take my first equation and try to solve for y. So if I try to solve negative 7x plus y equals 32 for y, I'd have to add 7x on both sides, and we'll get y equals 32 plus 7x. Here's where the substitution comes in. Now I'm going to plug that in to the other equation. So where I have a y in my second equation, I'm going to replace that with what y equaled, 32 plus 7x. So if I rewrite it, the second equation was 2x plus 3, and replace the y with what y equaled, 32 plus 7x equals 27. Now we have to solve this equation to find out what x is. 2x plus, do the distributing, 96 plus 21x equals 27. Combine like terms, this will be 23x plus 96 equals 27. Subtract 96 on both sides. To cancel that out, 23x equals negative 69. Divide by 23 on both sides, and we get x equals negative 3. Now we know what the x value is that satisfied this system of equations. Last thing we need to do is go back and plug it in to check what y would be. So if we return to our original equations, we're going to take our x of negative 3 and plug it in and solve for y. Both equations should give us the same result. As I work through this, negative 7 times negative 3 would be 21, plus y equals 32. Subtract 21 on both sides, we get y equals 11. Now we could check that with our second one. If we plugged it in and solved, we would also get y equals 11. So the final answer is that these two equations are going to intersect, have the same solution of x is negative 3 and y is negative 11. That's substitution. Last example, elimination. The goal of elimination is to try to combine your equations so that something cancels out. If I multiply my entire second equation by negative 4, let's see what happens. Negative 4x plus 20y equals negative 40. I'm going to use that instead, now that I've multiplied, as my two equations. If I took both of these equations and tried to combine them or add them together, we can see what happens. 4x plus negative 4x cancels out to be 0. That variable x has been eliminated. That's how I picked the negative 4. You want to pick a number to multiply one equation or both equations by so that a variable, when you add them together, can be eliminated. So the x's are gone. Now I can continue adding the y's. 2y plus 20y would be 22y, and 7 plus negative 40 would be negative 33. Divide by 22 on both sides, and we get y equals negative 3 over 2 or negative 1.5. Once we plug that back in, our problem is done. So we can pick either one of our original equations or both and plug in a y of 1.5 to finish solving. So I'll take the first one, 4x plus 2, plug in the y, negative 1.5 equals 7, and solve for x. 4x plus negative 3 equals 7. Add 3 on both sides. 4x equals 10. Divide by 4. X equals 2.5. And we get our final answer. These two lines would intersect or have the exact same values when x is 2.5 and y is negative 1.5.